Oh, definitely. That's gonna be cool.
All right, so let's come time and it's available and taking a look at it will hopefully become very clear by the end of today's lecture, and we'll discuss it some more tomorrow in the topic session. All right. So again, just to quickly review, we're have our introduction to quantum field theory, and we should understand that the degrees of freedom of the fields are what we call modes, okay? And in particular, a normal mode is an example of a mode where the amplitude oscillates at a fixed frequency, okay? And so the normal modes are simple harmonic. Each degree of freedom, each mode is its own, if it's a normal mode, is a harmonic oscillator, okay? And again, we've been reviewing it just over and over again because I want to get to this in your minds clearly. The simple harmonic oscillator, classically, this is the solution of harmonic motion once we've taken out the units, okay? Everything is in dimensionless units and the characteristic units, okay? And the X and P here are what we call the quadratures of the oscillator. And we can also think about the oscillation having an amplitude and a phase, and the amplitude and phase are, of course, related to the quadratures. If we think about it in phase space diagram, okay? And very importantly, we want to write this oscillator equivalently in terms of the real part of a complex amplitude. So the complex amplitude has as its real and imaginary parts the quadratures, okay? The way we defined it here, it has this 1/√2. We just have to keep track of that. And the complex amplitude evolves in phasor space by just accumulating a phase that goes clockwise, like e to the minus I omega t. So that we can equivalently, it's exactly the same thing. We can think about phase space equivalently as phasor space. It's the space of the complex amplitude where the real and imaginary parts of the complex phasor are the position and momentum quadratures, the X and P quadratures, okay? Right, okay. And the quantum case, we quantize the field by just saying that the conjugate variables are now quantum variables which satisfy the canonical commutation relation. H bars have been absorbed into the characteristic units because the characteristic length times the characteristic momentum is H bar, okay? And importantly, the complex amplitude now becomes a non-Hermitian operator, which these canonical commutation relations have this form, and that's why we stick the √2's over there, so there's no 2's here. These are the raising and lowering operators. So the eigenstates of the Hamiltonian are the number states, the number operator is the dimensionless square of the amplitude. Okay, the square of the amplitude is alpha star alpha. So A dagger A is the square of the amplitude in units of H bar omega. So we're quantizing the amplitude, right? The amplitude, and the square of the amplitude is the energy. So we've quantized the energy, okay? So we should make these connections. The number states, as we discussed, are the A and A dagger are the ladder operators that raise and lower me through the space from 0 to infinity. phase conventions, and thus the nth eigenstate I can achieve by applying the raising operator n times to the ground state and normalizing it. And that normalization is that, and everyone should memorize that. Okay? If you don't, or if you haven't already memorized that. Right. And so the eigenstates of energy are not eigenstates of position and momentum, so there's uncertainty in each of them. They're actually equal, and the uncertainty product for the nth eigenstate is this, particularly for the ground state, it's a half. That's the minimum possible uncertainty product one can have, okay? And the fact that the the energy eigenstates are not eigenstates of position and momentum is to say that there's a probability amplitude to have an x or a p. That's the wave function, right? That's the probability amplitude. The square of it is a density because it's a continuous variable. This is a probability density. And the wave functions you solved in wave mechanics, they're Gaussians times Hermite polynomials. For the ground state, this is the constant, and so the wave functions are Gaussian. There's a Gaussian fluctuation in the quadratures in the ground state. Okay? Right, good. So what we then said is that the field, so for example, we've been talking about this vibration field with some mode functions plus it's connected. Bless you. Where these normal modes depend on the boundary conditions. So if we have hard-wall boundary conditions, these are standing wave modes. If there are periodic boundary conditions, then we have traveling wave modes. And so we have what we call the positive frequency component, although it has a minus, but that's just how it goes. And this guy can have a plus. This is the negative frequency. The positive frequency component has the annihilation operators, and the negative frequency component has the creation operators in it. That'll become important later. Yeah?
Summation's over K, right?
The summation here is over K.
Is that
some number of modes.
Is it eta C? Or?
Yeah, that's the characteristic scale. That's the character way I haven't defined what that is. We'll talk about it specifically in the case of the E&M field soon.
Is that also dependent on K though?
Yes, it's true. It will generally depend on K as well. Yeah. Let's be more careful. It will generally depend on K. In the same way that, X there, it will be dependent on omega sub K, right? And remember, so what this length scale is for the mass in a potential is basically the 0 point motion, right? That's the characteristic scale of length in the problem. Okay. Good. So in particular, what we were saying at the end of last lecture was that the Hilbert space is what we call Fock space. And assuming we have no constraint on the total energy of the system, it's an infinite dimensional Hilbert space, which is the tensor product of the Hilbert spaces for each of the normal modes. In this case, that's one way of expressing that, okay? Each one of these is a simple harmonic oscillator Hilbert space, which is the Hilbert space that's associated with square normalizable functions on the line. Okay, that's L2R if you want to be pedantic. I don't want to keep it in. Right. So, in particular, the Fock space is a basis for the Fock space, is what we call Fock states. Now, every state in Fock space should be called a Fock state, but I don't make up the rules, much as I always want to. And when people talk about Fock states, what they mean is the basis. So that is, we have the tensor product of the basis of energy eigenstates for the harmonic oscillator. Yes, we were.
Does the K run to infinity? Like
It
your
does.
tensor product thing?
Runs to infinity. Yeah. In principle, you know. I mean, one could ask, you know, when you start getting down to the Planck scale or something, is there a fundamental minimum length or energy scale in the universe, and is there some cutoff of the maximum, the shortest possible length scale in the universe? But we're not worried about that.
So you both have like an infinite number of K and an infinite number of N.
That's right.
K.
That's right. Lots of infinities. Yeah, Omar.
If you consider cavity,
Yep.
anything is finite and it's not.
No. So if I have a cavity or just hard walls, this is mode, the first mode. I can have infinite wavelength.
So it becomes countably infinite.
It's countably infinite. So whether it's hard wall or periodic, by putting boundary conditions on, we discretize the modes. So really, this should be a Fourier integral, but we've turned it into a Fourier series so that we can count the modes. But in principle, we really should. I mean, what we often do in doing these problems, and you've probably done them, you know, when you studied black body radiation in your thermal course as undergraduate, is you put things in a box and then you take the box going to infinity. Probably did that problem. It's a standard way. And that's just so we can count things and then take limits. Okay, but importantly, what we think about, how we think about these Fock states, so we have N1 quanta of excitation in mode K1. That's what that means, okay? Which is to say that there are the quanta of excitations for this problem, for this vibration on a spring, are what we call phonons. So a quantum of excitation is a particle, okay? It's an individual unit of energy of the field. That individual unit of energy of the field is what we're calling a particle. And it has the properties we think about, that we imagine in our macroscopic world of, you know, a particle as something that is a indivisible entity that has certain physical quantities, okay? And we'll come back to this. Phonons can have energy. They can have momentum. They can have angular momentum. We can think about whether they do that. They might have spin. These are the properties of the particle, okay? We'll talk more about what those properties are in a moment. So I can have different states. This is a basis of the Hilbert space. That is an example of a state in this Hilbert space. But I could have states that are superpositions of the basis states. I don't have to be in one of the basis states, right? So, you know, I could example have a situation where I had superposition so I might have a state, let me just write it this way, which is, say, 1 over root 2, 1, 0, plus okay. When I write it like this, all the other modes are in the 0 mode, so I don't have to keep track. If I just am looking at 2 modes, I'm assuming all the rest of them are in the ground state. Okay, so I'm allowing for excitation of a phonon in either mode 1 or mode 2. Okay, so I ask you, as we discussed yesterday, how many phonons are there in this state? Is the number of phonons definite, uncertain? Definite. And how many? 1. We have definitely 1 phonon. We don't know which mode it's in. So this is an eigenstate of the total number operator. The total number operator is the sum of all the number operators. This is a 1 phonon state.
If we have,
Yep.
so the total number operator, is that our number of phonon operators then? Like how many phonons we have?
Yes, this is the operator which counts the total number of phonons in the field. We can have a state which is an eigenstate of the phonon number operator, or we can have a state which has an uncertain number of phonons. I could take a superposition of this with 2 phonons. That's a perfectly valid state. There's no super selection rule that rules out that I have an uncertain number of phonons in the problem. Yeah.
But it's not an energetic.
It is not.
So
It is
for
not.
fields, it's different.
So it will evolve in time, absolutely. So the two, if I started the solution, which was a superposition of, say, the first mode with, you know, this guy, then we would have some kind of phase. We'd have an oscillation between them. Okay, so absolutely, we can do that. I can think about the state. If I can think about, okay, so a few things I want to say, which is that the field theory is intimately related to many body physics. Because I can have multiple particles, right? So it's the theory of many bodies or many particles intrinsically. So there's an intimate connection. I mean, if you're doing condensed matter physics, if you're doing the study of many body physics, you are also doing quantum field theory, because the way in which we often describe that many body system is through an effective quantum field. Okay. Now, as I was saying last time, I can just, if I restrict myself to, let's say I have 1 phonon. Okay. If I have 1 phonon, which is not necessarily in a given mode, right? I could write that state as some superposition So let's look at this. What am I saying? If I didn't have the CCN, I've created 1 phonon in the mode K. But here I'm creating a superposition of phonons, right? This is a superposition of, you know, I'll just call it C1, I'll say not K1 because I don't want to have it right so much. This is the first guy with, you know, 1, 0, 0, 0, plus C2 plus C3 etc. Okay, this is a state where I have a superposition of all of these normal modes with a probability amplitude associated with one. So what's the probability to be in the kth mode? It's that, okay? And if I wanted to, if this was the state at time t equals 0, the state at a later time would be that. Each normal mode oscillates with that frequency, and that's what the state is at a later time. Now, when we have one phonon, this is a way of writing it, but we also, if you didn't know nothing about all this thing, okay, I'm racing your memories, you know nothing about this, and you wanted to write down the quantum mechanics of this particle with hardball boundary conditions, how would you solve but one? You don't know anything about field theory. You don't know anything about many-body physics. You don't know anything about A's and A daggers. Go back to your sophomore year of undergraduate, and you said, I have a particle in a box. How would you solve this problem? You write down the Schrodinger equation. There's a Schrodinger wave equation. You would then probably say, well, there are energy eigenstates associated. These are the energy eigenstates of the system. And you say, oh, there's a wave function. And my wave function I could write as some superposition of the energy eigenstates, which are the solutions to the Schrodinger equation that satisfy the boundary conditions, right? And in this case, you know, K, if this is 0, this is L, would be, you know, M times pi over L, where M is 1, 2, 3. So this is the ground state, this is the first excited state, and so forth. And if this was the state at some initial time, then the state at a later time is that, right? That's the solution to the Schrodinger equation. This description that we have, it's what is exactly the same thing, where each of these Fock states corresponds to a different one particle normal mode, okay? So this is the ground state normal mode, this is the first excited state normal mode, this is the second excited normal mode. There's a one-to-one mapping. It's an isomorphism. Every one of these eigenstates of my single particle Hilbert space corresponds to a one particle, right? This description of it is what's called second quantization. Because what I've kind of done is I've turned the complex amplitude into an operator. Yes?
When you write psi x of t, you wouldn't need to multiply that by psi x of 0? Or I guess
No,
you
I'm
kinda
saying
have it,
this
right?
is the state at time t equals 0.
Yeah.
What is the state at time equals a later time? It's this.
Yeah, it's that e to the minus I e sub k t over h bar times psi x of 0, right?
No. Every one of these have exactly the same superposition. This is the coefficient at time equals 0. This is the coefficient at time t. Every Fourier amplitude evolves at a certain amount of time. In this case, this guy evolves very simply. This is the initial value problem in quantum mechanics, or equivalently of a string They're exactly the same wave equation. We solve them exactly the same way. We decompose it into Fourier components. Every Fourier component gets a phase. So I can think about this operator, that's an operator, as creating a particle not in one of the energy eigenstates, but in a wave packet. This wave packet. So I don't have to create a particle in a normal mode. I can create it in any state, just like an electron doesn't have to be in an energy eigenstate. It could be in some superposition and have a dipole moment. The phonon doesn't have to be in an energy eigenstate. And I challenge you to the following thing. Suppose I look at two creation and annihilation operators for two different states. That this, let's say that this guy, so in this case, I'm going to use for first quantization, this is a notation we'll only use here, no one else uses this. Instead of an angle bar, I'm going to use a rounded bar, because this state is in the first quantized Hilbert space. This state is a superposition of the energy eigenstates like that. Okay, that's what that state is. This is its wave function. Let's say I have another state, which is some other superposition, right? Something else. Okay, that this is that. Plug it in. Use, do it. This is the sum over k and k prime, the commutator of d k a k with c k prime a k prime back. Okay, so I've plugged in the definition of these two guys. Each one of these guys is a weighted amplitude that way. Now what? Well, I take this outside okay, you with me? What is this? Let me write it down.
That's, yeah,
It's one, if k equals k prime,
So direct delta?
it's a delta. It's a Kronecker density. Okay? I should have emphasized that. The different modes commute. Which gives me which is this. Okay? So this is the formalism of second quantization. There's a lot more to say about it, and we don't have time to do a lot, but I want to just quickly talk about one very important feature of second quantization. Let's say I have a state which is, I have two phonons. One I'm going to create in the wave packet psi, and the other I'm going to create in the wave packet phi. Now, this is not necessarily normalized. I'm not going to worry about the normalize. The normalization depends on the overlap. Let's just forget about the normalization for the moment. Okay? Now, so what we just looked at, I mean, the CKs here were the amplitudes to be in the normal modes. Those normal modes are kind of like momentum. So I can think about the CK as kind of the momentum, this overlap with UK is the momentum space wave function of my particle in a box. It's really the energy wave function, but I'm being sloppy because I really want to deal with periodic boundary conditions. So now I want to ask, what's the two-particle momentum space wave function? Well, what I really like to ask, there's a K1 and a K2, and there's this, in first quantization, that's the two-body momentum wave function. There are two particles. It's a function of both K1 and K2. But I'm gonna, in second quantization, what that means is that state is I create a particle in K1 and K2. That's gonna be my momentum or energy eigenvector. So now I want to take the inner product between this state, 1K1, 1K2. I have one particle in K1 and one particle in K2. I want to take the inner product of this with this to say, what's the probability amplitude associated with one of the particles having this momentum and one of the particles having this momentum? That's my two phonon momentum space wave function. Let's take that inner product. When I turn the ket to a bra, my A daggers became A's. Okay. So that's what I'm going to call the two-body wave function. What is it? How would we calculate this? Now here is a trick of the trade. One of the tricks, whenever you're dealing with A's and A daggers acting on the vacuum, is you want to move all the A's to the right because they annihilate the vacuum. And all the A daggers to the left because they annihilate this. So I claim that this is equal to that. I can replace that inner product with its commutator because I can write the commutator is this times this minus the other direction. But that is zero, right? So when you have all the A's on the left and all the A dagger on the right, you can replace it by its commutator because the other term is zero. Okay? Now how do you take the commutator of this thing? Well, you gotta remember the commutator product rule.
Back out.
Well, that's dot products. That's another one. But this one, what you do is, I take this guy out. Plus so that's one term, right? I take it to the left, whatever that operator is, I take the other guy to the right. But when this acts on zero, I get what? When the annihilation operator acts on that.
Just zero.
Zero, so I'm going to forget about that. Okay. And so similarly over here, this is a dagger, sorry. Okay. So now I'm going to have this guy. And now I have well, let's do it one step at a time. Okay, so what I did is I took that guy off to the left, and now I have to add this guy into the right. Oh God, this is tedious.
Commutator algebra.
Yeah. Oh, let's see, what did I do? What did I do? I took that guy to the left, and now I have this guy. Did I do that right, folks? You agree with that?
Sure.
I'll agree.
Say yes.
Yes.
All right, well,
Yes, Professor.
I think it's right.
Yeah.
Okay, so now, what is this?
0
Well,
plus A and A.
This is the inner product because of this rule. Where is it? That one. The commutator of this is that inner product. And when I do this, I then can replace this with its inner product. That's the inner product of K1 with phi. Okay? Similarly, so when all is said and done, this is a lot of algebra. I get the following. I get this one is a psi. Psi of K1, phi of K2, plus psi of K2, phi of K1. The algebra on this takes some while to get used to, but I want to focus on the final result. Yes?
Should that be
Should one of
A dash?
those on the bottom be psi?
This is a psi, this is a phi.
No, I meant in the box, the final result.
Yeah, the final result, yes. Should be a, correct, thank you, Nate. Okay, let's focus on the final result. When we had one phonon in a certain wave packet, we said there is a momentum or a position space wave function associated with it. Now I have two particles. One of those particles is in wave packet psi. The other particle is in the wave packet phi. But which one is particle 1? And which one is particle 2?
Yes.
The answer is exactly what Nate said. We can't say. These are identical particles. And so because they're identical particles, we cannot say which is particle 1 and which is particle 2. Particle 1 might be in this wave packet and particle 2 might be in that wave packet, but I don't know which one is which. So actually maybe particle 1 was in phi and particle 2 is in psi. Now the fact that this, and this is an equal superposition when we normalize board 2, the fact that it's a plus sign here was something, a wool that I pulled over your eyes. And I pulled over your eyes by saying that these things were commutators rather than anticommutators, which is to say that these are bosons. They're bosons means we must symmetrize the wave function and it picks up a positive sign. So the phonons are bosons. And the reason is because their spin is 0. they have no spin because this was a scalar field. And because it's a scalar field, there is no intrinsic direction to it. The phonons are spin zero objects, and thus they are bosons by the fundamental relation between spin and statistics, which we can't derive until we do quantum relativistic quantum field theory. But because I assumed this relation, that the different modes commute is saying that we've assumed a bosonic statistic. Yes?
So when you write in your bracket, you're saying a hat k2 comma a hat bracket 5, that's the inner product?
This?
No, your very last line. I'm saying in your very last line.
Yeah, what I'm saying, okay, so there's a lot of horrible algebra that's not, this is something I just wanted to show you. We're not gonna get into this here. What do I mean by this? So this is A in the state UK commutator. So I've created one particle or annihilated one particle in that wave function. That commutator is the inner product between those two wave functions.
You see, that's what I'm getting at. Should I
And
not-
so this is that.
But you don't need a dagger on the other one?
This is an operator, and that commutator at the end of the day, what I'm saying is a number.
With your inner product for K2 and phi. There shouldn't be an A dagger there with A hat K2.
Oh, yes. There should have been a dagger.
And so that's essentially like a Slater determinant, right? When you're writing.
Yes. So, okay. So let me try to back up.
Sure.
Algebra craziness.
You got me with that one,
daggers.
man.
It takes
Man.
time, okay? The essence of what I want you to come away with in this is twofold. When you deal with identical particles, you have to deal with the symmetrization or anti-symmetrization of the orbitals.
Mhm.
If they're fermions, like electrons, in an atom, you have Slater determinants
Yes.
because those are the things that the determinants do the anti-symmetrizing. That formalism is called first quantization, where we write down wave functions and we have to, by hand, make sure everything is anti-symmetrized, like through the Slater determinant. However, the formalism of second quantization takes care of it for you. When I write down the state, I didn't have to write down a Slater permanent or a Slater determinant. I just said I created one particle in this wave packet and one particle in that wave packet. I'm not telling you which is which.
Yeah.
There are two of them. When I were to try to ask if I were trying to measure some probability amplitude, this amplitude through this mess of commutator algebra gives me the symmetrization for free.
That's pretty cool.
Yes?
So those results that we get, that side of K1 side, that symmetric boson,
Yeah.
that is a wave function.
That's a wave function.
So-
It's a wave function is a probability amplitude. It's the probability amplitude for finding one of the phonons with this momentum and the other phonon with that momentum. That's what this is.
Well, I guess what I'm trying to get at is since normally when you take the inner product, these are always going to wave.
Exactly.
Yeah.
So when we write down the momentum space wave function in wave mechanics, that is this inner product. This is, if I had a two particle thing, I would say there's a P1 and a P2. And that is that. A wave function is a probability amplitude. It's the amplitude to find that particular outcome, in this case, a momentum. So that probability amplitude is one of the phonons has this momentum and the other phonon has that momentum. And what we found is that it's the symmetrized thing. Yeah, Nate?
Suppose I'm crazy and I wanted to try it with 3 wave packets, would you get a result which is just the sum of all the different permutations?
You would, indeed. Be crazy. Do it. Yeah, it's a good exercise. Yeah. So, the bottom line of this is that, in this case, the phonons are bosons, but using the Fock space and second quantization formalism, we don't have to symmetrize all the wave functions. The commutation algebra takes care of that for us.
It's pretty slick.
It's very slick.
Yeah.
On the other hand, if I had electrons, then I would have to use the anti-commutator for that. Yes?
So when we do non-relativistic, non-field theory stuff, like in quantum mechanics, in undergrad too, we are told at some point, oh, this is a fermion, this is a boson, this has to be antisymmetric, this has to be symmetric. And I don't ever see proof for why that is. I remember that just being stated. Is that commutator the same thing? Are we?
We're just stating it. Yes, we're stating
Okay,
it.
it doesn't actually pop out.
It doesn't, no. We did that because of this connection between spin and statistics.
So does that ever pop out of somewhere, or is it?
It
just
does.
observed?
But to do that, we need relativistic quantum.
That would pop out of the Dirac equation.
Yes, and just more generally through the Lorentz symmetries and the Poincaré symmetries. So the connection between spin and statistics comes out of Lorentz invariance. We otherwise we're just putting it by hand. The fact that I said these different modes commuted rather than anti-commuted, I did by hand. That's where the wool, I didn't say, well, they're like independent degrees of freedom, and independent degrees of freedom commute. But that's only true if they're bosons, if they're identical particles. All right, great. All right, so, gotten some of that under our belts, or at least we packed it in. Now I want to talk about the electromagnetic field.
So, what field did you just quantize?
We didn't quantize a fundamental field. We quantized the field that's associated with the elastic motion of this many-body system. So it's really more of a condensed matter thing. If I had a lattice of atoms, I could think about phonons in a crystal, right? So they're what we call quasi-particles. They're not fundamental particles because they're not fundamental fields. They're fields that arise out of the collective of the whole of the condensed matter. So we just quantized the elastic motion of a string, or equivalently the elastic longitudinal motion of a rod. That's the field we talked about.
We could have chosen a different scale.
We could have. It's nice to talk about things on a string because we can think about that. Okay. Okay, so now we're going to talk about the electromagnetic field. What's the first thing when you talk about that? What equations should you write down? Maxwell's equations. Okay. So we have the electromagnetic field. And in particular, we want to talk about the free field. But the free field is where all the sources, the charge and current density, are zero. That's what we mean by the free field. It's free from interaction with anything else. Okay? So now I want to write down Maxwell's equations for the electric and magnetic field with no sources. Okay? You know how I'm looking at. those of you who took 511 with me last semester, what are my equations? Del dot E with no, is equal to 0. Del dot B is always 0 because we don't got no magnetic monopoles that we know of.
I love your optimism.
You gotta stay optimistic. Del cross E, Faraday's law.
Negative del T E.
Yeah, and in the units we will use, and because you're stuck with me in Gaussian CGS units, which are the right units, you gotta 1 over C. And del cross B, Ampere's law, but with Faraday correction is yes. Very good. So in these units, the units of E are equal to the units of B. They are the same in CGS units, which is why I prefer these units. Okay? So these are the equations. This is the classical electromagnetic field. These are Maxwell's equations. And we know in the vacuum, when there is no free field, that when we can decouple these equations by taking the cross product again, and that tells us that every Cartesian component of either E or B satisfies the wave equation in 3D. Right, with a phase velocity, that's the speed of light. Very good. So this was just like what we started. We had the wave equation for, the motion of the elastic rod or the string, and then we broke this up into its normal modes, right? So again, we can break up the solution into its normal modes for either the E or the B field. Let's do it for E. And so I can think about the normal modes which have that oscillation. So I'm going to take that ansatz and plug it in. Okay? So every normal mode has some spatial dependence and oscillates at that frequency. And when we plug it in, say for the E field, we get so the normal modes satisfy this differential equation, which is called Helmholtz equation. Okay. Now there are lots of different solutions to the Helmholtz equation. They also will ultimately depend on the boundary conditions, but a nice solution are the plane waves. Okay, so we can write down a solution which has some vector that depends on, and in fact now, because this is in 3D, I have to think about my modes having labeled with 3 indices, a kx, a ky, and a kz. So those are the modes, and if I wanted to normalize them, so if I have periodic boundary conditions, so I imagine I have a box that's really a 3-dimensional torus. It has some length Lx, some length Ly, and some length Lz, but this face is periodic with that face, this face is periodic with that face, this face is periodic with that face. So V, the volume is Lx times Ly times Lz. And I would have Kx is equal to 2 pi over Lx times some index m being plus or minus 1, plus or minus 2, dot, 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 and similarly for y and z. So each one of the wave numbers I'm discretizing to make it accountably infinite as opposed to a continuum of Fourier modes. Yes, Don?
How'd you say the faces are periodic?
I'm just, this guy, the thing along X, this guy is associated with that guy is associated with that guy, the top is associated with the bottom.
Okay, so like you go out one
I
side.
go, yeah, exactly, I come out the other, yeah.
Is that the same M for all the different Ks?
No, I would have an MX, an MY, and MZ, because I could have every mode, each mode is independent. I've separated it. I can effectively write this thing as e to the I kx x over the square root of Lx plus e to the I ky y over the square root of Ly and times. So though that's the normal modes, I've separated it in all 3 dimensions, okay? It's a mode in 3 spatial dimensions as opposed to 1 spatial dimension, which we looked at for our string, okay? Yeah?
Is V?
V is the volume, Lx times Ly times L.
So our units here are like root.
Yeah, the units, schmunits, I need to put them back in ultimately, yeah. Really, if I want to normalize it, should be square, we'll come back to the units, yeah. But these are not the units of the electric field, I'll have to come back to that. Okay, so that's the electric field, however, these modes have to also satisfy, this is the solution of the electric field. It's proportional to this. It must satisfy Maxwell's equations. In particular, del dot E equals 0 means that the normal mode must satisfy that. Okay. But if I plug that in, taking the divergence, or when I'm taking any operation of the del operator on the plane wave, it's equivalent to multiplication by that vector. So this implies that I k dot u equals 0. When you do that divergence with vector calculus, and you play around with it, if you're not used to it, you should be. Okay? Which tells us, as we remember, that k dot this vector is 0. So the direction of the electric field, this vector, is perpendicular to k, which is the direction of propagation of the plane wave. Okay? So we're looking at plane wave modes which are transverse. That is to say, the direction of oscillation of the electric field is transverse to the direction of propagation. That follows from Maxwell's equations. Okay? So our normal modes are vector valued fields, right? The value of u at x is a vector, because the electric field is a vector. So we're not talking about a scalar field anymore. We're not in Kansas anymore. We're in Oz. And in Oz, we got vector fields. Okay? The electric field is a vector field. But it's not any old vector field. It's a transverse vector field. Okay? However, once we have defined the normal modes of the electric field, we automatically know what the normal modes are of the magnetic field. Why? Because they must satisfy Maxwell's equations. Okay? And in particular, if I look at this or this, okay? So if I think about the normal mode of the let me call this this is the normal mode of the electric field. Let's look at the normal mode of the magnetic field. The normal mode of the magnetic field must oscillate with the same frequency because it has to satisfy Maxwell's equations. If E is oscillating like e to the minus I omega t, B must also. Can you see that by taking this through? Because otherwise it won't satisfy either Faraday's law or Ampere's law. So the magnetic field has the same time depends. Now we need to ask about its space dependence. Oops. I plug in the equation that relates them either through Ampere's law or let's start with Faraday's law. The electric part of the field must be related to the magnetic part of the field according to Faraday's law. If I plug in the form of the field there, what this tells me is I replace this ik, the del gets replaced by the vector ik, because the derivative acting on the exponent does that. Crossed into this u, e to the ik dot x minus omega kt equals I omega k over c dv. So what this tells me is that the normal mode of the electric field is related to the normal mode by the same mode function, but just with a vector in a different direction. This is just classical E&M, plane wave 101. E sub k here is k divided by the magnitude of k. And the magnitude of k is omega over c. So, to remind us, if I have a plane wave, this is the wave vector, which is the direction of propagation. This is the electric field, and where's the magnetic field? It's perpendicular, which is K cross E, epsilon. This, of course, is the polarization. Okay. So, the first thing, after all this rigmarole, is that we are decomposing the electromagnetic field into plane wave modes. So what we're doing a Fourier decomposition of the plane wave modes with periodic boundary conditions, which discretizes what the wavelengths can be in all three directions.
A lot of times when we have our, like, in our free space Maxwell equation waves, we're off by a phase, right? We're not, like the E field and the D field oscillate, but by a...
No, they're in phase with one another. If we had a standing wave, that would be different, but for traveling waves, yeah, they're in phase, yep. But good to remind ourselves of these things, yeah. Yes, we did that hard, probably, yeah. Okay, so, very good. So, there's one other thing. If we want to talk about the modes, what about the possible directions of the electric field vector? What we said is that the electric field vector must be perpendicular to the direction of propagation, so must be the magnetic field vector with this right-handed system. But I can have, if we want to think about all the possible modes, I need to think about a basis of possible directions of the field. So if I think about, oh God, can I not draw perspective? It's horrible. This is perpendicular to these guys, okay? This is coming out of the board, this is the plane perpendicular to it. God. All right? So I can think about two linear polarizations, say one that's horizontal or one that's vertical. But in general, I can also think about, since this is I'm thinking about a complex amplitude, I can think about circular polarizations, right? So I can think about something which is either right-hand helicity, or what we call positive helicity or negative helicity. That's another basis. So my modes are actually denoted by another index, which is the polarization. And without normalization, or I'll put it with normalization, so now I'll have, 2 pi q over v bless you. Where mu, that index could be horizontal or vertical, or right or left circular. Two different orthogonal polarizations that span the space of vectors in the complex plane as we described. Those are my normal modes. They're more complicated than the normal modes we had for the phonons. They're more complicated for two reasons. One, we're in 3D, no longer 1D. We have X, Y, and Z directions. Moreover, it's not a scalar field, it's a vector field. Moreover, that vector field is constrained. The vector cannot be in any direction, it must be perpendicular to K. Those are all the aspects that we have of this, okay? And so when we look at this, so by the way, what we have is that we choose this such that these guys, if they're in the same direction, they're orthogonal. Those are, say, right and left circularly polarized light propagating in that direction are orthogonal vectors with the star. Okay. So moreover, if I look at the integral these guys are orthogonal. They're orthogonal in their direction, and they're orthogonal when I integrate over all space. And that's because the plane waves are orthogonal functions in space. And then once I get k equals k prime, I'll get this delta function.
Is there supposed to be a prime on the conjugates K for the polarization?
Yes. No, there is not. They're only orthogonal if they're in the same, right? Because vectors corresponding, right? This guy should be star.
Yes.
And that one's supposed to have prime and K.
That, absolutely, yeah. Okay, yes.
Is that supposed to be x prime?
No, it is not. Thank you. Absolutely not. Yes. Okay. We can now write down the quantum for every normal mode. We have harmonic oscillator. HC stands for Hermitian conjugate.
Space was demoted again?
Poor space. So let us take a look at this. This has all kinds of fancy do's and da's and vectors and u's, but it's basically what we wrote down for the phonons. Every normal mode, there are creation and annihilation operators. What was in classical physics a Fourier decomposition of the field into Fourier components, in this case the Fourier components are transverse plane waves. Now we've said those amplitudes that tell us how much we have of each of the Fourier components is a creation or annihilation operator. Okay? We haven't yet defined the units. What are the characteristic scales? What we know is these guys are equal because E and D, because we've used God's units, I'm playing the role of God. And so these are the same thing. What it is, but let's just before we quit. What we know is that the energy of each one of a particle in a quantum of excitation, which is called what?
Photon.
A photon. A photon is a quantum of excitation. In the EM field. I can create a photon in a plane wave mode, or in a pulse, which is a superposition. I can have one photon in, it doesn't have to be in a plane wave, because we just said I can have a particle that's in a superposition of the modes, right? I can have a pulse that has exactly one photon in it. It doesn't have to be a plane wave. Could be a wave packet, just like an electron is a wave packet, which we studied. I can create, and the Fock space will be the tensor product of the harmonic oscillators for each of the modes. The modes are defined by both the polarization and the wave vector. The polarization must be perpendicular to the wave vector, but it's anything that's in there. We typically take a basis thereof. But just before we quit, what if we wanted to estimate what is the electric field associated with one photon? What we know is that the energy of a photon in a normal mode what's the energy of one photon in a normal mode that has frequency omega? H bar omega. How is the energy of the electromagnetic field related to the electric and magnetic field? What is the energy in the electromagnetic field? E squared. Yeah, the point of it comes about the flow. There's the energy density, right? And then the, oh God, we gotta remember, yeah, we forgot all that. But the energy is the integral over all space of the energy density, which is E squared plus B squared over 8 pi in God's units. Okay? Well, I'll call this H, the Hamiltonian. That's the Hamiltonian. We'll come get to this later, but I didn't know. But, okay, if I have one photon in this quantization volume of volume V, then basically this is the characteristic scale over times V. That's the characteristic electric field scale times the volume is the amount of energy, effectively. There's factors. So the strength of the characteristic electric field is the square root of H bar omega over the volume. That's what's going to go in there, up to some factors. That's where the square root of V comes in. So the strength of the electric field is such that the square of the electric field is the energy density. The square of the electric field is the energy density. Energy density is H bar omega divided by the volume. We've quantized the field. Please laugh. Yeah. All right. Very good game. Let's get out of here. I'll take questions outside.
So now instead of eta plus and eta minus, do we have E plus and E minus?
Exactly.
That's sick.
We should back off of it. Yeah, there's no like funding for it. Doesn't make any money.